Our last topic of your module 2 is your phase separation. So as the name clearly states, we're looking at the separation of components of a mixture into different physical phases, whether it's your liquid to vapor or your liquid to liquid. So first off, we're going to be looking at the phase separation occurring via distillation. So this is where we're separating your components because they have different volatilities, which is based on them having different boiling points. Okay? So your volatility is governed by your vapor pressure. So under your vapor pressure, Raoult's law comes into play. By definition, we obtain the partial vapor pressure for components in a mixture by taking its mole fraction, the number of moles of that component, divided by the total number of moles, and multiply that by the vapor pressure of the pure component. So here we have a mini example. Your total number of moles is 3, so for your respective solvents, you have 2 out of 3 times that pressure of that solvent, and 1 out of 3 times the other. The vapor pressure that you keep hearing about is the pressure exerted by a vapor when it's in dynamic equilibrium with its liquid in a closed container. So let's say you have liquid water in your closed container. If you were to increase the temperature on this water, you're increasing the kinetic energy of your system. So now your particles are gaining enough energy to break away from the intermolecular forces of your liquid, escape the surface of your liquid, and essentially become vapor. When they become vapor, they now hit the top of your container. That creates a saturated vapor pressure. Because all of your vapor particles are now at the top of your container, they cannot escape your container. So there's a build-up of pressure. Eventually, they are going to condense and fall back into your liquid. A dynamic equilibrium gets set up when the number of particles escaping your liquid is equal to the number of particles falling back or condensing back into your liquid. This is in contrast to your open container where your particles of your liquid break away from your liquid and become vapor. So they evaporate out until all of your liquid is gone. It is important to note that even though there's an increase in temperature and kinetic energy in both of your closed and open system, a liquid only truly boils when its saturated vapor pressure is equal to the atmospheric pressure. So your water would boil at 100 degrees Celsius in regular 1 atmospheric pressure, but if you were at the top of Mount Everest, your water is going to boil at 70 degrees Celsius because of the change in the atmospheric pressure. So now that we've looked at your vapor pressure and we also looked at Raoult's law, Raoult's law also describes the behavior of an ideal solution. So an ideal solution is essentially a miscible liquid. It is one where your intermolecular forces between your solvent and your solutes are the same as the ones in your mixture. However, we also have your immiscible liquids. So these are going to be considered your non-ideal solution. It is important to note that ideal solutions don't actually exist, but some mixtures come as close to ideal as possible. So you're going to take a look at them now. Now we have our visual to represent your ideal mixtures or your ideal solutions. So let's throw some letters into them. Your A to B represents your ideal mixture, and the intermolecular forces in this mixture is the same as the intermolecular forces in your pure A, and it's the same as the intermolecular forces within your pure B. So that means when it comes to forming your ideal solutions, there are no enthalpy or volume changes. So the same amount of energy it took to break the bonds in A and to break the bonds in B, the same amount of energy is going to take to form your bonds in your A to B mixture. And that is what makes it ideal. However, once again, ideal mixtures do not exist, but some come as close to ideal as possible. Note these few examples. Now we're looking at your vapor pressure composition graph. So we have the mole fraction of where your B is 1, that's the highest amount of B, and you also have the highest vapor pressure associated with your B. So you can tell from this information that B is your more volatile component. On your right hand side, you have the most amount of A, but a lower vapor pressure for your A. As you move from the right to the left of your composition curve, the mole fraction of your B increases, and so does the vapor pressure. So your B is your more volatile component, meaning it has a lower boiling point. So the intermolecular forces of your B are weaker. So a lot of the particles are becoming vapor, and these vapor are exerting out that vapor pressure. So the intermolecular forces of your B are weaker, so it breaks at lower temperatures in comparison to your A, which will have a higher boiling point. So while the vapor pressure of your B is increasing, the vapor pressure of your A is not increasing because it doesn't have enough temperature for those intermolecular forces to break, and you end up with all of those vapor particles. Notably, the experimental measure of your vapor pressure is very difficult, so your boiling point composition curves are used to compare your different components of your mixture. By comparing your two diagrams, you can note that the relationship between your vapor pressure and your boiling point is inversely proportional. So here you have your B, which has a higher vapor pressure, meaning that your B has a lower boiling point. Your A would have a higher boiling point and therefore a lower vapor pressure. However, for your non-ideal mixtures, you have two types of deviation. Your first one is your positive deviation, and this is where the actual vapor pressure is higher than you would expect. And this has to do with the fact that the intermolecular forces of your mixture is weaker than the intermolecular forces of your components used to form that mixture. Let me bring in some letters. Alright, so you're making your mixture of your AB. You make your mixture by mixing your pure A and your pure B. The bonds that are forming between your A and your B are weaker than the bonds that were present in your A to A and in your B to B respectively. So now, because your mixture has weaker intermolecular forces, it requires less energy to break those weaker intermolecular forces. So therefore, it's going to have a higher vapor pressure, a lower boiling point, and a higher vapor. Here are some examples of your positive deviation, and we're going to be looking at your water and ethanol in just a few moments. But first, where you have the maximum amount of B, you have a low vapor pressure, versus where you have the maximum amount of A, you have a high vapor pressure. So your A is a bit more volatile than your B. However, where you have the combining of your mole fraction, so where you have a little bit of A and a little bit of B, there is the highest amount of vapor pressure. So that is telling you that when you're forming your A to B bonds, these bonds are very, very weak, resulting in that high vapor pressure. Next, we have your negative deviation, and this is the opposite of the positive. So your vapor pressure is going to be lower than you would expect for an ideal solution under Raoult's law. And now we're going to bring back in those letters again. In this case, the intermolecular forces of your mixture are stronger than the intermolecular forces between your pure A and your pure B. Because the intermolecular forces of a mixture are stronger, it requires more energy to break these bonds or these forces. Therefore, your mixture is going to have a higher boiling point and a lower vapor pressure. An example of this that we're going to look at a bit more later on is the mixture of your nitric acid and your water molecule. The intermolecular force that exists within your ions that are formed from this mixture is actually stronger than your respective forces in your water and your nitric acid, and that has to do with the attraction between your oppositely charged ions. Some other examples include your chloroform and your propanone, your chloroform and your diethyl ether, and that has to do with your mixtures being able to form those strong hydrogen bonds that did not exist in your individual solvents. So we just looked at your two types of deviation of your Raoult's law, your negative and your positive. Let's go into a bit more detail when it comes to distillation. So starting off with your positive deviation, this is between your ethanol and your water. You're going to notice the boiling point of your ethanol is 78.5 degrees Celsius. The boiling point of your water is 100 degrees Celsius. And on your left side, you have 100% water, and on the right side, you have 100% ethanol. So let's say you're starting off with a liquid composition of C1. You take this mixture, you boil it at your given temperature of, let's say, T1. Boiling it at this temperature gives you a vapor composition that is richer in your ethanol. So ethanol is your more volatile compound, meaning that your vapor is going to contain more of your ethanol. You can collect some of that vapor. Whatever is not collected is going to trickle back down your flask and recondense in your flask along with the rest of your mixture. And this is known as your C2. Your mixture, your liquid composition of C2 is then going to be boiled again at your given temperature of T2. This is going to give you a vapor composition that is richer in your ethanol. And this entire process of your recondensing and your reboiling of your mixture is going to keep giving you a vapor composition that is richer in your more volatile component, which is your ethanol. And you're going to keep doing this and keep doing this until you eventually hit a barrier. Now this barrier is where you're only able to collect a maximum 95.6% ethanol. And that is because your vapor composition and your liquid composition actually interconnect there and they actually meet. So that means that in your vapor, you're going to have 95.6% ethanol. And in your liquid, you're going to have that same amount. So no matter how many times you boil and recondense this mixture, you cannot exceed your 95.6% ethanol. This is known as a constantly boiling mixture or your azeotropic mixture. And this particular mixture boils at your 78.2 degrees Celsius. So lastly, we're going to be looking at your negative deviation involving your nitric acid. So if you start off with your distilling of your very dilute nitric acid, you're starting off with a composition of C1 and you're tracing through what happens. Because it's dilute nitric acid, the vapor that is produced is actually richer in water than your original acid. If you condense the vapor and reboil it, the new vapor is even richer in water. So in your fractional distillation column, you're able to collect your pure water from the top of your fractionating column, right? And as the acid in your flask loses more and more water, it becomes more concentrated until you hit that barrier of 68% where your vapor and your liquid composition are the same. So you cannot collect more than 68% by mass of nitric acid from dilute acid by distilling it. So if you were to distill nitric acid more concentrated than 68% by mass, we are now looking at your right composition curve. So you're starting at a composition of your C2 to the right of your azeotropic mixture. So in that case, the vapor formed is richer in nitric acid. If you condense and reboil this, you get a vapor that is still richer in nitric acid. If you continue to do this all the way up the fractionation column, you'd end up getting pure nitric acid up the top. As in far as the mixture in your distillation flask, it is gradually losing nitric acid. So you're going to end up with a very dilute mixture within your flask due to your water. Right. So you can produce your pure nitric acid from the concentrated acid itself, greater than 68%, but you can't do it from your dilute nitric acid. So what we looked at today was the Raoult's law and the principles of your ideal and your non-ideal solutions, and whether or not they deviate from your Raoult's law. So this information can be used to explain the principles on which your different type of distillation is based. So we have your simple, your fractional, your vacuum, and your steam. I went into it a bit more on your fractional distillation in terms of your negative and positive deviation. So you're going to look at more of your examples in our next class.